Okay, our second speaker this morning is Professor Vieregg from the University of Chicago, and she's going to talk about neutrinos of 1,000 times higher energies.
Great. Can everybody hear me? We switched microphones, so okay. So I just want to thank first the organizers. I know it's a lot of work to put together a great conference like this, and so thank you to everybody. So I'm going to talk about radio detection of the highest energy neutrinos, and the caveat is I'm going to focus on radio detection. There's other ways you might try to detect the highest energy neutrinos, or at least neutrinos at higher energy than IceCube has thus far. But radio is something that's near and dear to my heart, so that's what I'm going to focus on. So for those of you who haven't seen 1,000 talks like this, I'll just spend the first 2 or 3 slides talking about why we care, basically. So, why might you look for ultra-high energy neutrinos? So I think about it that in the way that neutrinos are really the ideal high-energy messenger. So if you want to learn about the universe at ultra-high energies, neutrinos really are, in my opinion, your best bet. So neutrinos allow you to probe very distant sources that you can't see in any other way. Francis talked about this with a very different looking plot. But the way I like to look at it is that this is a plot from Auger. So this is the cosmic ray spectrum. And the only thing that you really need to know is that at 10 to the 20 eV, we've seen cosmic rays. So that's cosmic rays with an enormous energy. And that's indicative that there's stuff going on in the high energy universe that we'd like to learn about. But we'd like to do that with a messenger that allows us to look far and point back at sources. So that's neutrinos. So neutrinos open this unique window onto the universe. It allows for the highest energy observation of extragalactic sources. It allows you to look at very distant sources, sort of on cosmological scales. It also allows you, I think this is kind of neat, to look deep into opaque sources, right? So if you're doing photon astronomy, I think of it as you're sort of doing source dermatology, right? You're sort of looking at the outside of sources. But neutrinos are this nice particle where if they're emitted in the middle, they interact weakly, right? So they can come all the way out, and we can learn about what's happening, not just sort of at the edges, but in the middle. And so from a sort of cosmology perspective, we'd like to ask and answer the question, how does the high energy universe evolve over time? So how are ultra-high energy neutrinos made? Well, one way that they're made is through the GZK process. So this is just a simple sort of standard model particle physics interaction where you have cosmic rays, which we've measured, right, that interact with the CMB, which we've also measured. It goes through a delta resonance, and then eventually it gives you neutrinos. So one of the decay chains gives you neutrinos. The other decay chain gives you photons. But basically what this means is we know we have cosmic rays, we know we have the CMB, and this gives us this nice neutrino beam. So it gives us this nice accelerator and a target and this nice neutrino beam that we can use to try to do physics and learn things like discovering the origin of the highest energy cosmic rays and neutrinos. We can ask the question, what is the high energy cutoff of our universe? So what are the sources out there that are making the highest energy stuff? And what is the high energy cutoff of the universe? And maybe we can learn about what are the acceleration mechanisms inside of those sources. So how are we going to do this? So the way we're going to do this is by looking for radio emission. So when ultra-high energy neutrinos interact in a dielectric, a dense dielectric, or any dielectric, I guess, but it's more probable that they'll interact in a dense dielectric, they give off radio emission. So the way this works is a neutrino comes in, it makes an electromagnetic shower, and if the wavelength that you're looking at is big, so the radio waves we're looking at are this big, so if the wavelength that you're looking at is big compared to the size of the shower, you get this nice coherence effect. And coherence is a trick that comes up over and over in physics. And in this case, what it does is it gives us this nice boost in power. So it means that for high energy events, so for showers greater than about 10 to the 16 eV, the radio component is actually the strongest part of the emission. So that's what we're going to look for. And this is what the signal looks like. So this is actually an observation at SLAC 10 years ago now, where we accelerated a bunch of electrons, slammed them into a target, and looked to see what happened. And you can think of this basically as, this is electric field versus time, but this is basically what it looks like when you plug it into an oscilloscope. So you have this fast, impulsive broadband signal, and that's what we're building these experiments to go look for. So then you can ask yourself, well, what kind of experiment do you need? So hopefully I've convinced you that this is interesting and that there's a emission mechanism to look for, but it hasn't been done yet, and so the question is why? And the answer is that it's really hard. So neutrinos, we can just run sort of a back-of-the-envelope calculation, right? So what do we need? If there's one neutrino, GZK neutrino per square kilometer per year, which is just a guess, then we have an interaction length of about 300 kilometers. So that's actually relatively short for neutrinos, right? Because these are really high energy, so they have a short interaction length. But that means that we only expect about 1/1000th of a neutrino per cubic kilometer per year. So that means we need many cubic kilometers to try to detect these things. And that's hard. So you can't build that in a lab. So you have to go to some naturally occurring medium. And it turns out that ice, after a bunch of investigations in the field, looks to be the most promising. So the reason ice is most promising is that it's dense and it's radio transparent. So this plot on the upper right just shows, as a function of frequency, the attenuation length as a function of frequency. And basically, the measurements come in at, for good, clear, clean glacial ice, come in at about 1 kilometer. And so that means that's actually sort of surprisingly, amazingly transparent. It means that you can put your detectors pretty far apart, right, and still see neutrino signals from a large volume. So that's what a lot of experiments are doing in the field right now. So this is a nice sketch of a few different experimental concepts. So there's sort of 3 concepts on this plot. One is ANITA. So that's this one, where you have a neutrino that interacts in the ice, it makes a shower, and then the radio emission comes up to a balloon. So ANITA's on a balloon. Another thing you might try to do is put antennas sort of below the sort of snowy layer called the firn at the top of a glacier. And you look for neutrino interactions again. They make a shower, and then you see it right in the ice. And a third thing you might try to do is actually put antennas sort of near the surface of an ice shelf. And then you look for radio emission from neutrinos that are actually downgoing, and then the radio emission reflects off of a saltwater interface at the bottom. So if you pick just the right place, then the radio emission will bounce off just like a mirror, and then you get this nice boost in collecting area. So that's sort of 3 different concepts of experiments in the field and what people are trying to do. So this is kind of where we are right now. So the best limit at above 10 to the 19.5 EV is from ANITA. So these results are pretty old at this point, actually. But ANITA 1 and ANITA 2 flew quite a while ago, but this is still the best limit above 10 to the 19.5 EV. So if you want to sort of push at the highest energies, this is a good way to do it. So ANITA is a balloon-borne experiment. This is a 5,000-pound NASA long-duration balloon payload. And what these white things are antennas. So these are antennas that have 2 polarizations. And basically, you use this thing like an interferometer. So you record the signals and digitize them at the Nyquist frequency. And then you use this thing like an interferometer to point where the radio came from, and then eventually try to point where the neutrino came from. Once you launch this balloon, this is the balloon, it becomes the size of a football stadium. And here we have our tiny payload at the bottom. But here's the results from ANITA 1 and ANITA 2. So it's actually very boring. So ANITA 1 saw 1 candidate on a background of 1, and ANITA 2 saw 1 candidate on a background of 1. So I like to say we're really good at estimating our backgrounds. Okay, so here's where we are right now. So these are sort of models and current constraints. This plot is maybe 1 year old. But here we have ANITA right at the very highest energies. Off the plot on the right, you could also point a radio telescope at the moon and make limits way out at even higher energies. But here's ANITA out at high energies. And then at lower energies, you see IceCube and Auger, right? Those are the experiments with the best limits at a little bit lower energies right now. And of course, IceCube also has this beautiful detection of neutrinos at the PeV scale. So what we've done so far is we're constraining models already. So it doesn't actually look that way from the plot, right? So as you constrain, as an experimentalist, right, you work hard and you constrain some models, and then the models go off the plot. So it looks like, oh, we're just touching all these models, but really we're sort of making progress over time, and those models go off the plot. And it looks like we have something like another 2 orders of magnitude we'd like to get in order to build a real ultra-high energy neutrino observatory and do great science. So the last bullet point is why bother? It's not a fishing expedition. So there is, although albeit a low, floor somewhere on the flux. And so there's a lot of reason to believe that with another 2 orders of magnitude-ish in sensitivity over current limits, we could have not just a detection, but a real working observatory that would have lots of events, and we could do particle physics and astrophysics and cosmology. Okay, so what kind of detector is interesting to build? So, of course, this is my personal biased opinion. So when I try to think about what are the 3 science goals we're after, this is how it boils down in my head. So the first thing is I'd like to know what the high energy cutoff of the universe is. So I'd like to measure the highest energy particles in the universe. So that's going to be neutrinos, hopefully. The second thing you might do is try to reach some of these more pessimistic models by getting a factor of about 100 in sensitivity over where we are now. And then the third sort of more outlandish thing to try to do with radio is to measure the astrophysical neutrino flux measured by IceCube, right? But you see these become upper limits here. So we'd like to try to figure out a way as a field to build a detector that could extend that observation to higher energy and provide nice energy overlap with IceCube and really build this sort of coordinated high energy neutrino observatory. So I'm going to start from the highest energies and work my way down. So at the highest energies, right, so what do you need to build if you want to place the best constraints at the highest energies? So the way you do that is on a balloon. And the reason you do it on a balloon is because from a balloon, you can see lots and lots of ice, right? And in order to see the highest energy neutrinos, they're so rare that you have to see lots of ice. So in the last few years, we've actually had 2 more flights of ANITA. Relatively recently, just this past year, we had a flight of ANITA. And there's going to be a few talks on this on Friday. So Cosmin is going to talk about the ANITA 3 search. And then there'll be a few talks on ANITA 4, which I'll get to on the next slide. But ANITA 4 was actually a really great flight for us. So we had this really nice new programmable notch filter that helped us. And we've recovered the data drives and analysis is underway. So this is, we expect that we'll continue to have world-leading sensitivity at the highest energies. And we also actually expect to see hundreds of cosmic rays at energies greater than 10 to the 18 eV. I haven't talked at all about cosmic rays, but ANITA can also see cosmic rays through a radio emission channel. And also, the other thing that's kind of interesting about balloons is that the thing that balloons suffer from is decreased lifetime, right? So you can only fly 30 days every 3 years. But that means that per unit time that they're up, they're really quite sensitive. So if you want to have sensitivity to transients during that time, balloons are actually a pretty nice method to do that. So there were a lot of improvements for ANITA 4. Oindri Banerjee is going to talk about that, as well as Andrew Ludwig. This is just a sort of snapshot of where we are in calibration. So we've worked through a lot of calibration for ANITA 4. Here's a plot of sort of our pointing resolution before you do a bunch of calibration and after. So once you do all your calibration, your pointing resolution, remember this is an interferometer. So the pointing resolution gets a lot better after you've calibrated everything. And then the plot on the right just shows that compared to ANITA 3, where we basically got swamped by some satellites that had launched between ANITA 2 and ANITA 3 and were squawking radio at us. We were more clever in ANITA 4 and put these programmable notch filters in that allowed us to achieve a much higher lifetime fraction. Okay, so that's what's going on at the highest energies right now. So then the question really is, how do we get that factor of 100 and build that real ultra-high energy neutrino observatory? So that's where a lot of people are focusing, I think, these days. And this is just a schematic, sort of just an overview slide of why you'd go to the ground. So balloons are great at getting to the high energies and looking at transients. But if you want to really get a factor of 100 at sort of the heart of the GZK cosmogenic neutrino regime, you basically have to go to the ground. And so the reason you have to do that is because you get more live time. You have a little better control over your background because you're not moving around the continent randomly. You have a lower energy threshold, right? And everybody knows as you push your energy threshold lower, you get more and more events because everything's a falling spectrum. You can make your detector bigger, right? So on a balloon, you're stuck with what's inside the launch envelope. But if you go to the ground, you're in principle not limited by that. But the downside is that from a balloon, you can see 700 kilometers in every direction, but from the ground you can't. So right now, you know, we've actually as a field spent some time looking at a variety of ideas to think outside the box, but people have basically settled on Antarctic ice as the best detector because of its nice radio properties. So that's the ARIANNA and the ARA experiment. So ARIANNA is an experiment that is being built on the Ross Ice Shelf, which is sort of near the edge of Antarctica. An ice shelf, I know way more about glaciology than I ever thought I would. So an ice shelf is something that has water underneath. So what that is, it's floating on top of the ocean. So there's a bunch of water at the bottom, and a neutrino can come in and interact, make radio, that then bounces off this nice mirror at the bottom up to your antennas. And it's like having a secondary collecting mirror at the bottom. It's really, you know, a nice idea. ARIANNA can also see potentially cosmic rays, right? If you point antennas up, you can see cosmic rays. And also there's this channel I'll talk about in a few minutes of this Tau neutrino channel, where if a Tau neutrino interacts in a rock somewhere, here it's pictured in a mountain, then it could go through a charge current interaction, give you a tau, and then that tau can make an air shower, and you might be able to see that as well. So ARIANNA right now has 7 stations deployed in what they call the hexagonal radio array. This is a schematic of the layout, so this is 7 stations deployed. They also actually have 2 cosmic ray stations, so those are stations with antennas that point up. And they've actually seen some cosmic ray candidates. So here's some result that I saw at the ICRC. That's a result of a template search, where you make a template of what you think cosmic rays should look like, and then you do a search, and they found quite a few cosmic ray candidates that look quite nice. So that's what's going on with ARIANNA, and Chris will have a talk as well on Friday if you want to hear more details about ARIANNA. So the full ARIANNA station, so right now there's 7 stations, the full ARIANNA array would consist of something like 1,200 stations. Remember that these stations are sort of relatively easy to deploy. They're near the surface, and so 1,200 is not a crazy number. And you know, another thing, and this is a plot of projected sensitivity if you ran a full ARIANNA for 5 years. And you know, another thing that's sort of interesting that's going on this season is that ARIANNA is going to deploy a surface station at the South Pole this season. So in November and December this year, you know, I said there are experiments at the Ross Ice Shelf, but they're going to come to the South Pole and deploy a surface station there to sort of see what the site is like. And it may actually turn out that a combination of surface stations and South Pole is a good way to go. So this is happening in coordination partly with ARA, who's providing power, and working together on calibration. So that's, I think, a good path forward, and a good sign for a path forward in the field that we're sort of working together on power and calibration of ARA and ARIANNA this year. Okay, so this is ARA, the Askaryan radio array. So this is sort of, I think, the sister experiment to ARIANNA, right? It's a slightly different idea. So ARA is at the South Pole. Instead of having antennas near the surface, it has antennas down a hole. And the reason you might go down a hole is because that fern, that snowy layer near the top, does weird things to your radio, and it makes it hard to detect. So it sort of refracts the radio, we think, it refracts the radio rays away from you and makes it hard to detect on the surface. So we have chosen to put our antennas down a hole. So this is what it looks like. We have antenna clusters down a hole. We have calibration antennas. And basically, a neutrino comes in, makes radio waves, and we try to look for it. So the Askaryan radio array, the idea is to eventually build something like 37 stations of antennas buried 200 meters below the surface. And currently, there's 3 stations and a test bed deployed. And we're actually going to deploy 3 more stations this coming year. So in 6 or 8 weeks is the shipping deadline, and we're going to send all the hardware down then. So there's going to be 2 talks on Friday as well from Brian and Carl on ARA on Friday. So this is some projections from ARA and the first results. So ARA, maybe a year, I forget exactly when, put out the first results from ARA stations. And you know, although the limits that 2 stations for 1 year can put out are not competitive with IceCube and Auger limits, it's a good sign for the field, right? So it shows that we've it's a demonstration of end-to-end analysis tools and shows that that our projections are scalable, right? That if we do what we say we're going to do, which is deploy 37 stations and run for 5 years, then we can get the sensitivity that we hope for. And so this is the projection from ARA these days in terms of where we might get. Okay, so then the last sort of more outlandish question, I think, is, it'd be really nice to build this factor of 100 in sensitivity, but I'd like to, see if we can extend the IceCube observation to higher energies. So how are we going to try to do that? So, the question really is, can we push the energy threshold down? Because radio has this problem, right, that the coherence effect means that the coherence effect that makes the radio waves means that it's a strong function of energy, right? That like you really need a high energy shower to get significant radio. But can you push the radio threshold down? So there's obvious reasons why you might want to do this. And so the question you ask yourself is, how do I get the highest signal to noise ratio in my antennas as possible? It's a really simple question to ask. How do I get, the biggest signal to trigger on? And I think a good answer to this question, although maybe not the only answer, is to build a phased array. So that's something that people have been thinking about for a while in the field. And it's a beautiful solution. It's an elegant solution to a problem where instead of triggering on each antenna separately, you combine them all together to make the equivalent of one high-gain antenna, and then you just trigger on that. So this is some, I'll admit, optimistic improvements in event rate based on a Monte Carlo that Keith Bechtel wrote a few years ago, of just a simple scaling argument of what happens if you phase together some number of antennas. What kind of increase in effective volume can you get? So I think the thing to look at is actually the table at the bottom. So if we have 10, 16 antenna stations, and don't do phasing, these are the types of event rates over 3 years we might expect to get based on different flux models. So this is one IceCube input flux model. That's an e to the minus 2.5. From the combined global analysis. And then, if you put in the e to the minus 2.1, that's from an upgoing muon analysis from IceCube. That's a little more sensitive to higher energies. That's an e to the minus 2.1, so that looks better for us, right, because it's a harder spectrum. And then there's a couple of different choices in GZK neutrino models. Okay, so if you go from 16 antennas and then just phase them, you start to see a significant improvement. And then if you ask the question, which is a totally crazy question, how many antennas do I need, to phase together to get significant numbers of PeV sort of energy neutrinos? If it all works perfectly and they all see the same signal, you need 400 antennas, which is maybe crazy. But this middle thing of 16 antennas is definitely not crazy. So that's what we're doing for ARA this year, actually. So we're deploying an 8-channel, actually, phased array on ARA. So we are drilling a hole right in the middle of an ARA station, deploying 8 V-pole antennas down the middle. ARA has built this sort of alternate trigger system and alternate front end to plug right into the ARA station, and we're just going to try it. So we're going to try it this December at South Pole. We've built a custom board for this. And we're just doing all the beamforming and all the phasing on an FPGA. And we're going to find out this year whether it works like it does on a piece of paper. And if not, why it doesn't work like it does on a piece of paper. Okay. So, in addition to sort of these experiments that are pushing forward like ARA and ARIANNA, there's, of course, IceCube, right? So IceCube, as Francis talked about, is a large optical detector. And IceCube Gen 2 is a proposal to expand that, right? To make its footprint bigger so that it can see more high energy events. And that, of course, is really interesting if you want to push to higher energy and might make this sort of overlap with radio more believable and interesting. But IceCube Gen 2 is also talking about a possible significant radio component, which would certainly be really interesting. So then I think the last section, the last thing you might try to do is look for radio emission from Tau neutrinos. So I focused mostly on radio emission from dense media, right? A neutrino interacts in something relatively dense, and then you just see the radio emission from that directly. But there's this other neat channel where a Tau neutrino interacts in a rock, and then you can't see the radio emission from that directly because rocks aren't radio transparent. But then the Tau neutrino, the Tau lepton that's made in a charge current interaction if it escapes that rock, it can make an air shower. And then you can see radio emission from that air shower. So there's actually quite a few people who are thinking about and trying to do this. So the nice thing about this is you can observe maybe from a mountain, from the surface, or from a balloon. And Steph Whistle's going to talk about one idea there on Friday. And it's also possible to do this with ARIANNA and ANITA, but it doesn't require ice, right? You can do it with these experiments that also look at ice, but but it doesn't require ice. So an experiment that's pushing forward on this front is called GRAND. And again, there's going to be a talk on Friday about this. So GRAND is an idea to put 200,000, a lot, of antennas in China. So this is the sort of drawing, and build a giant detector to look for this. So GRAND is deploying their first sort of prototype antennas this year. And they have sort of a really intriguing projection of where their sensitivity might lie. As you can see, it's an order of magnitude better than these other experiments, the projection right now. It's also 200,000 antennas. So in summary, so the observation of ultra-high energy neutrinos would open a new window onto the universe, and I think that's really, really interesting. The radio technique can probe a new energy regime, right? So we're trying to, cover the high energy regime from the highest energies down to hopefully PeVs, but definitely 10 PeV. And then the Tau neutrino channel is something that people are talking about more and more these days. So the Tau neutrino channel is promising and is accessible from a balloon, mountain, or surface configuration. So I guess I'll leave it there and take questions.
Thank you, Abby. Anybody has questions? Please raise your hand.
What is the source of the background in these detectors?
Yeah. So the source. So he asked, "What's the source of background?" I guess I don't need to repeat the question because everyone heard it. So the source of background is twofold. So one is thermal noise, actually. So in an ideal perfect experiment, your background would be limited by thermal noise. So what that means is that the ice you're observing is hot, right? It's at 250 Kelvin, and it radiates all the time, and every once in a while that fluctuates upward and looks kind of like a neutrino. And that would ideally be your background. There's also man-made backgrounds. So that's the second part. So experiments like ANITA that fly over Antarctica, and we've built a very, very sensitive radio experiment, and we can see 700 kilometers in every direction. We see a lot of man-made noise. So that's the other background. Man-made noise is, there's many ways to try to get rid of it. The two easiest things are, one, they tend to come from places where there are people, or where we know there are people, and two, they actually tend to not look like neutrinos. So they tend to look like CW or continuous wave, single frequency noise. So those are the sorts of cuts we use to try to get rid of those.
We have time for one more quick question. In the back. Or maybe, okay, maybe Stefan and then
Okay,
Yanis.
so brief question. Can you give us an idea of what's typically the cost associated with these type of arrays? I mean, for 1,200 radio antennas doesn't sound like a lot, but then it's the South Pole, so thank you.
Yeah, so costs are a funny thing. I think people quote the hardware cost in the single millions of dollars for these sort of an ARA or ARIANNA-like configuration, sort of $5 to $10 million. But costs are a funny thing, as you say, when you go to Antarctica, because a lot of it is, folded into logistics. But yeah, I think the hardware cost for ARIANNA or ARA is in the upper single millions of dollars.
Okay. Last question.
Is there any other way of improving the sensitivity besides the more lifetime that you are pursuing? For example, in the architecture of the detectors or something like that?
Yeah, so are there other ways to improve the sensitivity? So more lifetime is obviously one. And then the other thing, so it's all about two things, I think. It's all about how much ice you instrument and what the gain is that you instrument that with, right? So when I say how much ice, what I really mean is solid angle. So if you can instrument more volume or come up with a clever way to increase solid angle, you win there. And also if you can figure out how to have the highest gain, effective gain antenna that you can, that's where you win big time, I think. Yeah.
Well, let's thank Abby again. And